Hi everyone, in this video I'm going to talk about a few ways to choose the regularization parameter beta. So recall from the last video that beta, in order for our regularization scheme to converge, we needed this condition, that beta decreases as eta to the p, where p is between 0 and 2. So one way of choosing beta is so at the end of the day, what we want to do is fit the data within the noise and then stop. That we can't really do much beyond that. So the L-curve idea here is to fm beta minus the data squared, say, and this is m beta squared. So we have we're minimizing, right? We minimize over m of fm minus d. fm minus d plus beta times the norm of m squared. And so this is our data misfit, and this is our penalty term. And so the idea is that you sample different values of beta so this is, say, beta 1, beta 2, beta 3, beta 4, and so on, so that you can trace out this curve where you plot so your vertical axis here is your penalty term, and the horizontal axis is your actual, how close you're fitting the data. And so it says to the L-curve, not principal, pick beta of maximal curvature of this plot. And the idea here is that I'm fitting, it's essentially a trade-off. So this is a trade-off, or it's a compromise between data misfit going to 0 and overfitting. Because remember, when that's basically this penalty term is what's preventing the overfitting. So right here would be your case, because if this is where you'd have your maximal curvature. And so the idea is that, oh well, I can actually get my data misfit to continue moving towards 0, right? But at the expense of getting a lot larger in this penalty term. So I don't necessarily want to do that. And similarly here, I can get my penalty term to decrease, but just very slightly at the expense of getting to not matching my data hardly at all. And the main advantage of this approach is that I don't need any prior knowledge of the noise. A disadvantage is that L-curve, it's not actually L-shaped per se. So actually finding this point of maximal curvature, you have to sample. How you sample it to find that, you don't necessarily know. And the curve might not even be L-shaped. What if it looks super shallow like that? You know, in that case, you're not finding an optimal parameter might not be easy. And so the also there might not be a theoretical it's not theoretically robust. And so this motivates Morozov discrepancies, the Morozov discrepancy principle. And what this principle says is we wanted, so we saw previously that E beta noise is less than or equal to order of the noise divided by the square root of beta. And so what we want really is for different beta, we plot our data misfit. And if we have an estimate on the noise, then we can sample different values for beta. So in the absence of beta, we're going to get closer and closer. Yeah, but we're going to fit the noise. So the point is, here I sample. As I increase beta, my data misfit will increase. But I find that beta that intersects this line, because once I start fitting below the noise level, what I'm really doing is I'm fitting noise. And so this beta will be the optimal one. I find that intersection of what I essentially estimate to be that level. And you might have an estimate on this because you know your instruments have certain specifications. You learn this from experimentalists or something like this. The downside is that, so the advantage is that it's more robust, but the disadvantage is that you need prior knowledge of the noise level. And so that concludes our mini section on regularization, but this will remain, these themes will remain here for the remainder of this series. So thank you guys for watching, and we'll move on to different topics after this.